And I just wanted to start out with a very high-level statement here that this work is a step towards building more comprehensive learner models, and that could mean many things to different people. But in this work specifically, we wanted to personalize math learning for students with different reading abilities. So we wanted to be able to predict that reading ability and be able to personalize student learning in our math software for students with different reading abilities. And just to introduce our software here, MATHia from Carnegie Learning is a personalized math learning software. It's an intelligent tutoring system. MATHia is used by over 600,000 middle and high school students across the United States. Students typically use it inside the classroom for 2 to 3 days per week. And content in MATHia is broken up into lessons, what we call workspaces. And these workspaces can be either what we call concept builders, which are more traditional lessons that every student goes through a fixed sequence of material to learn concepts in now, as well as what we call mastery workspaces, and these are workspaces that let students practice, give them practice opportunities on problems to learn or to master towards mastery of a set of skills. Everything that I'll be talking about in this talk concerns only concept builders. Here we have, as an example, concept builder in MATHia that is teaching students fractions, decimals, and percent conversions. Essentially, it gives students some text on the left, and then it lets them learn through some practice on the right. So what students have to do here is to convert between fractions, decimals, and percents. And I'll go back to this slide in a little bit too. This is an interesting workspace. Another interesting workspace in MATHia is called the pre-launch protocol. This workspace is the student's first interaction in MATHia. Every student has to complete it, and they have to complete it first. And it just teaches the student how to interact with MATHia, how to request hints, how to watch videos, how to use different features of the software. And it's just this introductory workspace. It doesn't really have any math learning in the process, but it just sort of familiarizes students with MATHia and how to do work in MATHia. So here, it gives students some text about how to use hints, how to look up unknown terms in the glossary, ask for a hint, etc. And then here on the right, it's asking students, I'm thinking about an animal that starts with the letter E, what is it? And it's not an elephant, it's not an eel. I don't even remember what it is, but it's something that you have to request a hint for because it's so such a uncommon math. All right, and then to introduce the data that we used for this project, so we had data on 2,600 middle school students from the Midwestern US state. And we received the students' math and English language arts end-of-year exam scores from the district. And then internally in MATHia, we record every interaction that the student has with MATHia. So we had almost 80 million actions in MATHia. And then 165,000 of those actions were in the pre-launch protocol alone. In the following slides, we only use grade 7 as an example, and grade 7 had the most data data, so it's a little over a third of that, of those numbers. And again, I mentioned the pre-launch protocol here because we assume that it is something that might be highly predictive of reading ability because it does not really have much to do with math. And in prior work from Liz Ritchie and others, they have assumed that the pre-launch protocol is a test of reading. But we're going to try to prove that. All right, so the first question we can ask with this data is how is MATHia content related to reading? Is it related to reading at different levels? And because we have the ELA test scores, we can use that as reading ability and see how performance in MATHia correlates with reading ability. But because content in MATHia is also related to math, and the students' math and reading abilities are usually also correlated, we needed to come up with some metric that takes that into account. So here, instead of just taking correlations between students' ELA scores and MATHia performance, we take a ratio of that over the students' MATHia performance and then math scores. And I haven't really defined what MATHia performance is, but we take it as the student's correctness on the first attempt for every step in MATHia. And then we take the z-score of that and we rank those workspaces from workspaces that are most related to reading compared to how related they are with math to the least. And we find that the pre-launch protocol is one of those that are most related to reading. That makes sense. That's a good sanity check there. And the one that was least related to reading compared to its relation to math was that workspace that I showed earlier about fraction, decimal, and percent conversions. And if you remember that workspace, it wasn't the case that it didn't have any words. It had a lot of words. But what the ask from the student was in that workspace is to just understand that table on the right and convert between fractions and decimals and percents. So once the student understood that, they didn't even need to read all that text on the left, that introductory text to be able to know how to solve that table. All right, so we looked at how content is related to reading at different levels, and the next question that we wanted to ask here is that now that we have that, we know that content is related to reading at different levels, can we use that to predict the students' reading ability can we build some data set and build a predictor on it to predict students' reading ability? Because we have some data about 2,000 to 3,000 students, but that's very difficult to get because that requires the district giving us that data, which is usually difficult. So we went and did some feature engineering. We looked at we computed these 4 features for every step in MATHia that we have data on. So we looked at the correctness of the first attempts steps. We looked at the number of attempts. We looked at just-in-time feedback. So this is when a student makes an error, and if it's a common mistake or a common misconception, then MATHia is going to give the students some just-in-time feedback. So how many times they received just-in-time feedback on that step, and then the number of hints that they requested on that step. You can think of other things as well, like the time it took for students to complete a certain step and things like that. Time is a little noisier because the student can go away into something else, having the software open or something like that. But yeah, these are the 4 that we came up with at this point. And then the target for the prediction were the students' achievement level on their end-of-year ELA scores. And this was between 1 and 5, where 1 and 2 were a failing score, and 3 through 5 or a passing score. And I do want to show the two-way tables and numbers because it could get a little boring, but just to like get an idea about how well these models work. We did some model exploration. We looked at several models, several machine learning algorithms here. We have, as you see, we have like SVM, a simple neural network, and lucid trees. And on each of the four set of features, we trained a different model. And then we took an ensemble of those, and that was a majority, the majority vote of those four models. And you see the SVM does a little bit better than the MLP, but when we looked at that, we found that it makes all of the predictions it makes on achievement level 1 were wrong. So we couldn't go with that, whereas MLP were making more reasonable predictions. And we're going to look at several confusion matrices in the following slides to show how those predictions actually look like. And then another metric that we looked at was the low median false positive rate. So predict that a set of students are below median on their ELA scores. How many of those are false positives? And the baseline here we used was the assistance score. So this is the number of hints and errors that a student receives. And on the P1 protocol alone, because that is sort of thought about as a unit test. So that was the baseline. The standard majority as a set was the ensemble here. And then the strong majority here was we only took predictions when 3 or more, so 3 or 4 of those predictors was weak. And we threw away all the other predictions, which can be useful if your goal is to have high quality predictions, but not necessarily to be able to predict on all of the students in the sample. And so we achieved down to 7% false positive rate on that. And here we're going to look at some confusion matrices. So what this is showing is that let's predict that a student is in achievement level 1. And then for every row, it's going to show how many of those predictions were actually in achievement level 1, how many in achievement level 2, and so on. And note that the color scales go to different ranges. And then all of the ones on the left are going to be the standard majority predictions, all the ones that are on the right are going to be the strong majority predictions. And as you see, most of those errors that it's making are within one achievement level. So if our goal was to sort of have a more binary classifier or pass fail or something like that, then this would be a pretty reasonable model to that. And this was on all of that concept building data. And again, the same here, but only for pre-launch protocol data. This looks worse because we went down from 8 million data points to 165,000 data points. But it's still pretty reasonable if our goal is to have some binary prediction, because almost all of those mistakes are within one level up or down from the tree. And all of these are normalized by columns so that every column sums up to 1. Which sort of answers the question of, within this prediction, how many fall within, how many of the 2 data points are within that prediction. And then one concern we had was that is our model only predicting, math ability, and because math and reading are highly correlated, we're not really doing anything new here. We're just predicting math. But we think that we're predicting reading. And this is a really important concern to have, because these are the students math and ELA score, and you see this is a very strong correlation here. So how do we know we're predicting above a certain line in ELA scores and not to the right of a certain line in math scores? And this is not like causal evidence, but we wanted to have some evidence that what we're doing was reasonable. So we looked at those predictions that we made and tested them against
Time saver. You just
so yeah, we found that our model is totally not predictive of math ability, which is great. As you can see, this is garbage, which is great. So that gives us some confidence there. And we're sort of looking forward into the future, into upcoming work, and we've already started doing some of this. One thing we can do with this work is to predict in real time students' reading ability after their first interaction with MATHia. So after the pre-launch protocol, this is just 10 minutes in, and we already have a good idea about the students' reading ability, so we can provide them with the supports that they need. And we can also look at historical data. We have many years of MATHia data, and you can see whether the trends are different for students with different reading abilities. That's all I have.
Thanks very much.